All right, so stepping into our first example here, we got a couple of capacitors, one with 6 microfarads, and then another with 3 microfarads. So I'm just kind of drawing it as we go. Are connected to a potential difference, so some type of battery or cell that has a potential difference of 18 volts. Now, it doesn't matter which direction your battery is facing, okay? Remember that current just goes through and it's in all places all the time, and so it doesn't really matter if current goes this way or if it goes the other way, it's all going to be the same. All right, so I just drew my battery in, doesn't matter which way it goes. So it says find the equivalent capacitance and find charge and potential difference for each capacitor when the two capacitors are connected in series, which is what I've drawn first, and then we'll do in parallel. All right, now you should be able to find the total capacitance. That's what we learned in the previous video, that when they're in series, that we do 1 over the total capacitance, which is going to be 1 over 6 microfarads plus 1 over 3 microfarads. Now what we expect is that the total capacitance should be less than either one of them on their own. All right, and so when we do the 1 over 6 plus the 1 over 3, we should get an answer of the capacitance is 2 microfarads. All right, so that's what we got total. Now the second part says find the charge and potential difference for each capacitor. All right, well, now that we know the total effective capacitance, we can find out how much charge is across those capacitors. Now this is where the understanding of how capacitors work is going to need to come into play. Remember, what's happening is we've got a positive here and a negative here, which means that we're going to end up having negatives go here, and we're going to end up having positives, sorry, not positives go there, we're going to have negatives go from here over to the positive side of the battery. And so we're going to end up having a positive here. Now, as this side becomes negative, it's going to push electrons away over to this side. And so I'm going to build up negatives, which is fine because this side is building up with positive charge. Not building up, but you know, the result, the net is positive charge. And so we end up getting a positive over on this side and a negative over on this side. Now, because those two are dependent on each other, right, those happen because of charges going from one to the other, which means that they should have exactly the same charge, right? The charge that exists on this plate is positive, dependent on how much charge electrons, how many of those electrons moved over to that plate. And so they have to have exactly the same charge. Now what that means is that we can use our equation from the formula packet, which was that V equals Q over C. And so we'll go delta V equals Q over C. And knowing the total potential difference, which is 18 volts, then we can find the charge that's on each of those because we know the total capacitance now. It's 2 microfarads. Now, all we have to do is solve for Q, and the Q that we get is 36 microcoulombs. And so that's the charge. That's the charge that needs to be across each of those so that the total capacitance due to the total potential is 2 microfarads. All right. Now we can use that because that is the charge across each of those capacitors. There's 36 microcoulombs on the left capacitor, and there are 36 microcoulombs on each plate of the right capacitor, right? One side is going to be negative, so this plate right here would be a negative 36 microcoulombs. This would be a positive 36 microcoulombs. Same thing for this guy, negative 36 microcoulombs and positive 36 microcoulombs. So that's the amount of charge that's stored up on that capacitor. Now, that having been done, we should be able to find the potential difference across each of those capacitors now, because we know how much charge is there and we know what their individual capacitance is. So if we look at capacitor 1, then capacitor 1, we can use that delta V, kind of like when we were doing the current and the resistance. We could look at the current and resistance for the whole circuit, but we could also look at current and resistance for individual pieces. So same thing here. We know what the total, we're going to use that Q over C. We know what the charge is. The charge is 36 microcoulombs, and we know what the capacitance of that guy is 6.0 microfarads. And so if we do that, then we should get a potential difference of 6 volts. All right, now we can do the same thing for the second capacitor, the 3 microfarad capacitor. And so we'll do that for capacitor 2 now. And so we'll go delta V across that capacitor is going to be the charge, which is that same 36 microcoulombs, divided by the capacitance of that one, which was 3 microfarads. And when we do that, we should get 12 volts. And you'll notice that as expected, that 6 volts and that 12 volts add together to give me the total of 18 volts. And so therefore, we've been able to find, using the principles and understandings of how capacitors work, we've been able to find out what the capacitance is of the whole circuit. We know how much charge is on those plates, and we also know the potential difference on each capacitor. All right, so hopefully that's helpful for you, and we'll move on to another example.